My name is Sebastian Vallejo Vera. I'm a professor at the University of Western Ontario. And boy, do I have some answers about some of the questions that we just had before today. Today I'm going to be talking about this sort of idea that I've had with a friend of mine about having this principles first approach to the application of large language models in the social science. And I'm not even going to try to link it to empathy, because I can't. But it is about large language models and sort of how we apply methods. Now, I just want to preface the talk by saying that this is based on a book manuscript that we couldn't have under contract, just a small brag there, which is co-authored with a friend of mine, really, Joan Timoneda from Purdue University. The working title is Large Language Models in Political Science, Theory and Application of Transformer Models. It's a very exciting title. It's not a workbook, but it is sort of an approach to large language models and the application of large language models in the social science in this sort of principles first idea that we have. And I'll explain to you a little bit where this principles first approach is. And we think this is like this framing is one of the pedagogical and also maybe methodological contributions of the book. So let me start by telling you a little bit how this idea came about. So this is one of the most infamous figures in transformers, machine learning, natural language processing from the Attention is All You Need paper. And this sort of like transformed the way that we understand natural language processing, one of the most cited papers. It changed everything. I've read this paper 50 times. I still don't completely get it, right? So I go through that paper and I'm like, this is cryptic and Byzantine. I had to look up that word. Half of the time I'm like, just, ¿qué chuchas is happening here? And, I insult in Spanish because that's my language. And when I go through this paper, one of the things that I realize is that this paper was not written for me, right? So this paper was not written for a political scientist. It was not written for a sociologist or for a social scientist. This paper was written with a computer scientist in mind, right? So it uses the language of information retrieval, right? So when it talks about query, keys, and values, I'm like, I don't know what that is. But if you ask somebody in the information sciences, they're like, yeah, that's information retrieval. That you should know this, right? So and I've spoken to some computer scientists, and they're like, yeah, no, I mean, they assume a whole bunch of things, and they don't prove a whole bunch of other things, but hey, it works, so what do we care? Like in the social scientists, we sort of care, like why the things work as well. This is not a diss on computer scientists. So one of the things that, going through and trying to understand, this idea of transformers is that even though large language models are advancing at an incredible rate, and that every single day you have new innovations and these things just seem to be getting better and better and better, the architecture, right? This transformer architecture is still sort of the underlying idea of how this architecture works still the same, right? So it's still sort of like built upon this encoder-decoder architecture, and that information is being like streaming through each token as it gets trained through different encoder layers. So one of the ideas that we had is, if we believe that, yes, large language models are going to continue getting better and better and better, but also are going to be less open, and we're going to have less of an idea of what's happening inside. If we understand these principles of how these large language models are built, then maybe we can also more purposefully use these technologies in our own work. A social scientist, any type of scientist, but I guess trying to address a social science audience. And one of the things that we look at when we look at this sort of architecture and these systems, we think about this being sort of like a collection of systems that have been put together. And because it's a collection of systems, there are different parts that we can modify that are going to help us extract, as much. I'm going to use sort of like the computer science language here, as much performance as we can from these models, right? So the question that we should be asking from this sort of principles first approach is, what systems get activated when what task, like depending on the task that we're doing, what systems are being activated. So maybe we can modify those systems and improve the way that these models work. Now, here I'm going to use some language that is going to be slightly different that I guess people usually think about these models. So I'm going to be talking about the encoder models and decoder models. Encoder models have fallen a little bit out of grace as of lately, I guess. But if you think about your BERT, your Roberta, your DBERT, that's how we call encoder models. And then your decoder models are your GPT models or your generative large language models. But they're both large language models, and we think that there's a place for both. So if we sort of go chronologically on how these transformer models have evolved, we first have the decoder-only transformer, like this causal self-attention models that were developed with GPT-1. And what they did was they were taking the transformer architecture on the left, and they were fine-tuning these models to be able to perform a set of different tasks. Right? So this was the first thing that they were trying to do. Now, future iterations of this work, GPT-2 and beyond, would pursue a more task-agnostic route and zero-shot and few-shot prediction through in-context learning, which I think is particularly important or relevant for the type of things that we do in the social sciences. So this is one route that large language models took, and you have to say the current state of the art is amazing, right? So every single day we are amazed, but the new things that they can do. One of the things that it's important to note, however, is that at inference, weights are frozen, right? So we are only working with most of these decoder models, right? So we're only working at the prompt level, right? At least for two of the tasks that we're going to be comparing today. So I forgot to preface this. So the two tasks that I'm going to be comparing this is going to be text prediction with an encoder model and text annotation with a large language model, which is sort of the question you were going at. Maybe I have an answer for you today, but I don't. So I'm going to compare these two things. These are two very specific tasks, very limited in terms of everything that you can do, and there's a whole bunch of other people that are going to presenting on other things that these models can do, but just to make a comparison between both of them and how the different levers that we can pull in this transformer architecture can help us improve performance. Now, so adaptation happens in the prompt. So whatever we can change is how we prompt these things. Even though fine-tuning is still possible with some open source model, with all of the open source models. And here's a shout out to one of the talks that's coming, I think tomorrow, with WIBA, for example. Right? Now, BERT, when it came out, was actually trying to solve one of the problems that the first GPT problems had. That it was the sequential setup from the generative pre-trained models was suboptimal for tasks that benefited from bidirectional context, right? So if I was trying to classify something and I needed information from both sides of the text, initially I wasn't able to do it with these causal models or these sort of decoder models. So they say, hey, what if we used all of the text, that is bidirectional attention, right? So we look at what's going to happen, like the tokens get information from what's happening in the past of a sentence or also in the future of a sentence, right? So they came up with these mask language models in where they would get a word, they would mask it, and again, this is from sort of linguistics and processes that have been done in for 60 years in trying to understand how readability works in text, right? So it's a closed procedure, right? Saying, okay, if I mask this word, then how likely are you to guess the correct word that goes in place of that mask? So they do that, and one of the cool things about these encoder models is that when we fine-tune them, right? So when we use them for inference, we can change all the weights, right? And really modify the way that each token is represented as we go through each encoder layer, and we end up with this model. So the pre-training of these models bakes representation into the weights, and fine-tuning updates these weights end-to-end, right? So if we have these two setups, that means that, and we understand how these systems are built, it means that we have different levers that we can pull and optimize depending on the task that we're carrying out. So what I'm going to do from now until the end of the talk is sort of show you different levers that we can pull on the encoder side, then some levers that you can pull on the decoder side, in these two comparable tasks, which is text prediction or like text annotation in the large language model side, or text prediction in the encoder side, and see how they compare and what we can do with each, right? So in the encoders, and I like to always think as encoders are very malleable, is that here are 4 levers that we can pull and that can help you, improve in your prediction task, and this might get some of the context that Lau was talking about before. And there's a lot of overlap with the two talks, and maybe tangible on the tangents, but I'll show you where. So we can further pre-train what they call domain-adapted pre-training or topic-adapted pre-training, where you can continue mass language model training on a domain corpus before fine-tuning, right? So I can take a encoder model, give it more data, make it understand a domain better, and that probably is going to help me, in my prediction. I can change the masking strategies, for example. So I know that masking is a system, so I can change the masking strategies, and maybe that's going to give me an upper hand when I'm trying to, predict or train these models for different tasks. There's even some calibration that you can do. I'll show you some work that we've done with MC dropout at inference, which accounts for uncertainty at prediction. And then we can also just remember that at the end of the day, these are machine learning models that are trying to minimize loss. So we can change even the way that this loss is minimized. So here is, for example, a comparison of models that are trained using Roberta on this is COVID prediction. We used an annotated COVID training set, and we just Roberta, and then we feed it a whole bunch of COVID information that the model didn't have because it was trained before COVID happened, and we can see how it increases performance. And then here, what we do is we change the masking strategy. We say, well, what are some high information words that the model probably needs in order to increase performance in this particular task, and probably coronavirus and COVID. So we're going to mask those a little bit more than the rest and see if it increases performance. It doesn't increase a lot of performance, but it does change the distribution of error in the classes, which might be something that you might want. Depending on the task. For the MC dropout here, what we're doing is during training, there's always going to be one neuron that is dropped out so you don't overfit your models, but that doesn't happen at inference. We allow that to happen at inference as well, and we test this when we're trying to, we build these models that predict DW nominate. These are ideological positions for members of the Senate in the United States. And we see that when we turn on this MC dropout, we increase performance. If we haven't done that, we go a step further and we say, well, this is not a class, this is a continuous variable. And this is just like a prediction. So we, instead of using your logit here, we're using a regression and try to maximize a mean square errors. But what if you don't have a lot of data like we had? Then we can bin this continuous variable, but this makes an ordinal class, not a multinomial class. So we're just very purposefully using an ordinal way to minimize the errors, which uses Coral, which is not the same Coral that you came up with that. What about when we use decoders? So when we use decoders, the parameters are frozen. So what we're doing is we're working mostly with the prompt. And of course, decoders can be further fine-tuned. And so it's a slightly unfair comparison that I'm doing here. But if you think about that, most annotation approaches using decoders primarily focus on modifying the prompt. So let's look at how you can modify the prompt. So you have the typical zero shot, few shot. And then we have something that we've sort of come up with called rolling in-context learning. So what does this mean? In-context learning means just keep the prompt from before in the prompt itself. So just if I label something at point first observation, then keep that in the prompt as much as you can. And we see that it does increase even over a few shot chain of thought in performance. One of the really cool things is that in some of them, we leave the answer. So this is the annotated answer. We leave the annotated answer. But here we didn't leave the annotated answer because in context learning, what's happening in the prompt is what you're telling the model is look for the correct task. You're not changing any parameters, so you're not training it in any way. So look for the correct task and give me the answer. So that makes sense here. We do not need to leave the correct answer because we're not training it to learn the correct answer. We're just training it or helping it reach the correct task, find the correct task in their memory, right? So we do that. We actually show that it improves performance as time goes by, sort of to the point that we're trying to make. And then knowing the levers, how do we choose, right? So how do we choose? We're using a large language model, or if we're using an encoder, for example. So one might be of performance and cost, right? So here's sort of like some estimated cost on how much it cost us to train a model to detect racism in tweets, in Spanish, different forms of racism, racist discourse. So something is very contextual. So obviously, the best performing model was the so when we used only 1,000 observations, these are labeled 1,000 observations, this is the performance, and the best one was GPT. But we actually had 3,000 observations. So we had 3,000 observations, and then we further pre-trained our model. The best one was Roberta, or XLM cross-lingual model of Roberta, which we further pre-trained. But obviously, it was much more expensive. The thing is that we had 2.5 million tweets. So at 2.5 million tweets, the cost of this raises, but the performance doesn't because it's exactly the same thing. But this cost doesn't move because once you have a trained model, you can pass as many tweets as you want through there. It's going to be the same. We actually had 2.5 million. If we have done that in GPT, that would have been the cost. It's not entirely clear what is the optimal sort of Pareto optimal behavior, but we think that it's going to be dependent on the task. So we came up with sort of like a taxonomy of tasks. This is very preliminary. These dots don't mean anything. I just put them there however I sort of wanted. But we thought about two axes, representational coverage and outcome ambiguity. So representational coverage, and this is something that we cannot really know, but it's like if we think about how the data was trained, like how the models were trained, what data it had, like how likely is the type of data that I'm going to be using, how likely is it going to be in that training data? And for example, for racist language in Ecuador, the likelihood is very low. For something like sentiment and topic classification, the likelihood is very high. So it might help you decide what model to use, but, and the principles is what allows us to make that choice. What route should it take? Well, let me look at all the levers that I can pull, all the levers that I can change these levers according to the task that's at hand. We have only covered two comparable tasks here, which is class prediction and annotation. We cover other tasks in the manuscript, but always fall back to the principles. So ultimately, this is what we argue, that transformer architecture provides the basic system on which language models are built, which is not a novel position, but it was not built with social scientists in mind, so we just sort of tried to fill that gap. So thank you, and I think I'm over time.
We have time for one, maybe two questions, if anyone has questions.
Not everyone at the same time, please.
I have a question about the F1, which is, at the end of the day, an average.
Yeah.
But in social science, we care about distribution. So
Yeah.
I argue that F1 is from a STEM degree that is developed. Mm-hmm. But in social science, we do not have correct or wrong answer to a survey about racial resentment. Mm-hmm. We need the distribution. And if the distribution is 1, like very racial resentment, 6 less, or vice versa, we want to see how many 1, how many 6. Mm-hmm. But here, we as social scientists, we are relying on a STEM F1 score, which can be misleading. I wanted to know what is your perspective on that.
So actually, that's an excellent question. Something that we've thought about and we argue for, which is we not only care about F1, but the distribution of errors. And one of the things that we found, for example, when we're thinking about the distribution of errors, is that when we change the masking strategies, we do not change the overall F1 score. It sort of remains the same, but it does change the distribution of errors. And that helps us decide whether it's worth it or not. So like you said, we care about the distribution. In this case, we care about having more, being better able at detecting fake because it was a harder to find category in our data as a whole. So I think that all of these questions get answered. Like it's not for me to answer. I guess it's for like this is an easy answer, right? So it's for you to answer. But here are like the principles that you can use in order to answer. But yeah.
Thank you.
All right, one more quick question.
Well, it's usually a terrible distribution. They get the mean right enough. Students get killed at versions.
Thanks so much for that. A really fascinating talk. We've been using a lot of NLP approaches in the lab to try to create stimuli, essentially, but also to do some studies on impression formation and intergroup kinds of dynamics. And we found masking to be really important, especially when we're looking at social media data. And so I'm just curious about that specifically, about masking and how fundamental you think. So of the 4 quadrants, do you feel like masking is a lever that really is vital, I guess, in terms of these encoder models?
So I think it is to a certain degree. So I think that masking helps you at the margins. So you have a model, you have a certain performance, and you want to increase it just a little bit more. We found that it helps, especially if you are using language that like you're adding a lot of tokens into the model, right? And that's something that happened here in this COVID study that we were replicating. It also happened in the racism study that we were doing. Like these were tokens that were like these words were not in the primo. So we added them. But then we also said, well, let's help the model sort of learn this because these are high information words. Like we know that these are high information words. The model did not know these were high information words, and it had a really hard time trying to link them to something else because again they were very contextual, specific to like where we got the Twitter data from. So I think that there, yes. Again, this is like a choose your right lever, and is the juice worth the squeeze kind of thing?
Yeah, especially when we've been comparing things like news stories to social media data, we find that masking really seems to be very important in these kind of like spontaneous, real world kinds of conversations. Really interesting, great talk. Thanks.
Thanks, Sebastian.